All right, everybody, it's Math 1151. Today's Friday. We're almost done. We've got 1 week and 1 day after this day left. And today we're going to talk about 5.4. So 5.3 was the fundamental theorem of calculus. And you may think, when do I ever have to know this? Well, I have a good friend, and on her job interview, they said, "Oh, I see you took calculus." And she's like, "Yep." And you know what they ask her next? What's the fundamental theorem of calculus? Yeah, that was a little rough. But remember, what's the fundamental theorem of calculus? It says this. It says, there's a couple ways to write it. Here's the way I'm going to write it. The integral from a to b of f of x dx is equal to capital F of b minus capital F of a. And this thing here, these things here, are the they're antiderivatives of f. And if I were you, and I were sitting here, I'd say, one thing that people often do is they say this, a common misunderstanding is to think this is what the integral means. A common misunderstanding is to think this is what the integral means. And it's not so bad to have in Calc 1, because every time you see an integral, you're pretty much going to want to do this. Pretty much. But what is an integral again? What does it compute? Signed area. It computes area. And perhaps the first thing we should talk about in 5.4 is this idea that it computes signed area. And they give you two tricks. One of which I think is pretty cool, and the other one I'm not real sure how you'd use it, actually. I look at it and they say, well, this simplifies. I'm like, I don't know. It's a little unclear to me. But the two tricks that they present in this section deal with odd and even functions. Odd and even functions. Now, we have odd and even numbers, right? Odd and even numbers, and every number is either odd or even. Is that true? Is 0 odd or even? 0's even, 0's even. And is -2 odd or even? It's even. Is 1/2 odd or even? I don't know. Okay, odd and even only makes sense for integers. And we have odd and even functions, and not every function is odd or even, but some are. And the ones that you'd really want to be odd and the ones that you really want to be even are this way. For example, x cubed, do we think odd or even? Odd, it's right, it's odd. This is odd. And x squared, that's even. If you have, it kind of gets complicated at some point, but these are the prototypical examples. X to the 5th, odd. X to the 6th, even. There's a geometric interpretation, though. And the geometric interpretation is so strong that a lot of times I think people just skip this part. But this is where the names come from. If you take x to a power, if the power is odd or even, that's what it tells you it is. So here's the geometric idea. Even functions, they're the easier ones of the two. Even functions have reflectional symmetry across the y-axis. Reflectional symmetry across the y-axis. So what we're saying here is a function's even. There we go. If it has reflectional symmetry across the y-axis, it means that when you go on the other side of the y-axis, I'm doing the best I can here, that would be the picture of an even function. All right? And think about x squared. Does x squared have reflectional symmetry across the y-axis? Yeah. That's even. What? What? Same with cosine. And those are the other two prototypical examples. I'll say it one more time. Cosine, so odd, you should think x to an odd power. Or sine of x is odd, and cosine of x is even. Now I've actually, by accident, told you guys why cosine of x is even. Cosine of x is even because later on, if you pursue calculus, you're going to learn that cosine of x is equal to, here's one reason, cosine of x is equal to 1 minus x squared 2 factorial plus x to the 4th over 4 factorial minus x to the 6th. What do you notice about all these exponents here? They're even. This is something to the 0 power, also an even number. And sine, this is not something you need to know. Don't write this down. Don't tell anybody I told you. Keep it a secret to yourself. Is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus, and so on, whatever. Yeah. Don't tell anybody. I know it's on video. Nobody watches them. So there we go. Even, odd, geometric idea. So there's the geometric idea of an even function. It's a reflection across the y-axis. Let's talk about odd functions. So an odd function, here we go. This one's going to be more difficult for me to draw and think about, unfortunately. That's okay. I'll do great. There we go. That's my picture. There's my odd function. Now, what happens here is it has rotational symmetry, 180-degree rotational symmetry around the origin. We're going to take this thing and we're going to spin it around. That's the sort of symmetry. So this is actually really good. This is reflectional symmetry across the y-axis, and this is rotation symmetry around 180 degrees counterclockwise around origin. Oh, and stupid Dr. Snapp. Does anybody know why I'm stupid? Yeah, I just wrote where I need to draw my picture. I'm just going to do it anyways. Yeah, sorry. Okay, so now, if I rotate this around, if I'm not mistaken, which I often am, it's going to look like, wait. Did I do that right? Yeah, that's right. That's right. That's right. That's right. Yeah, I'm drawing sine, and okay. So think about sine. Sine looks like this. If you draw sine, so this is a sine function. There's sine, and then there's the other side, right? There's sine, and it's odd. Odd. All right. So what? So what? Thanks for telling us about functions, Bart. You know, I didn't really want to know any of this stuff. I don't see what it has to do with what we're talking about in calculus. I'm just being some random person. So what's it have to do with calculus? What are we doing in calculus right now? We're computing signed area. Yeah, no question. Okay. Computing signed area. And the idea is if you have an odd function, if I have an odd function, well, my signed area is going to be really easy to compute if my limits of integration are symmetric about the origin, right? Because what's the signed area that I shaded in going to be? It's going to be 0. And so we have this complicated, maybe not even complicated, but this statement, and it says, hey, if you got an odd function, if you have some odd function, and of course math is sneaky, because if I said, hey, suppose you have some odd animal, that means it's like just some animal, right? So if I say, suppose you have some odd function, you might think I'm just talking about any function, right? But I'm talking about odd has a meaning here, right? This is that odd as just some odd function. The integral from minus a to a of f of x dx. F has to be continuous too, but that's not a huge deal. It only has, well, whatever. Equals, what's it equal if I integrate this odd function? 0. You're not going to encounter any situations where you have an odd function and you have that problem. So, odd functions are nice if you're integrating a symmetric interval, right? Great. 0. Even functions. Well, now if the function's even, we have no snazzy trick like this. You know, and in fact, I propose it as a challenge to you. And if I can give extra credit, which I don't know, I would love to give extra credit for this, but I don't know how. So you can do it and try to challenge me to give you extra credit. The integral from minus a to a, if f is even of f of x dx, then we can't really say anything cool like it's equal to 0. But what we could say is this is equal to 2 times the integral from 0 to a of f of x dx. And then one might say, well, that simplifies things a bit. I don't see how, and this is my challenge to you. If you could tell me why this is so much simpler than this, I would love to know, right? Because you're going to have to anti-differentiate this period. You're going to have to evaluate it at 2, right? And the function is, what type of function? Even. So could it be any harder to evaluate at -2? No, it's equal to the same thing, right? I don't really see how this helps very much, but if any of you can show me how it helps, I would love to know. I have no idea how that helps. Now the first one's solid. Second one, meh. It's nice to know, I guess. All right. I can't imagine how it would come up, but maybe I'm just not very imaginative. What questions do you guys have about this, even odd functions? How many of you have seen even and odd functions before? Well, that's pretty good. I'm sure I saw them before too, but I didn't remember seeing them when I first saw them. I distinctly remember not remembering them. Okay, so, the next topic in 5.4. 5.4 is kind of a hodgepodge of topics. So we have even and odd functions. I think this is all we really need to say. I guess we could do an exercise. Why not? Yeah, okay, that sounds good. Let's try to see if we can do an exercise. Okay, so here's how this problem comes up a lot. Tell me the integral from minus 100 to 100 of 3 x to how about 10 x to the 5th dx. What's the answer? 0. Right? What if I add 4 to this? Is it still odd? No. Think about it. If you add 4, it shifts the function up. It's no longer has symmetry the same way. Multiplying, okay. Adding, not okay. Can anybody give me a reason why multiplying is okay? It just stretches it. That's a good reason. Can somebody else give me another different reason why multiplying is okay? What can you do with the 10 and the integral sign? You can pull it outside, and then is anything in front of that? No, then it's your old function, right? So stretching, either way of thinking about. Anyways, this is equal to 0. I didn't have to do any calculations, just had to identify that it was an odd function. Very nice. All right. So now, any questions about this before I continue on? Because I'm going to change gears. It's just what comes next. So now, there's one thing that's near and dear to your hearts, I'm sure. Averages, right? We all want to know about averages. Now, by the way, if you want to know how to compute your grade, you guys know how to do this? You just go to the math, just Google 1151 OSU math, and it'll give you the home page, and you can look at the syllabus. And I believe something like, on the syllabus it says, don't quote me on this, it says something like 87 and above is in the A range, you know? So that's pretty good. So that means you can lose a lot of points and still be in the A range, you know? That makes me feel good. I don't know. You guys aren't smiling. Anyhow, you should look at that, and you can start to calculate your grade. And you know, the homework's out of 50 points, and the other part's out of 50. I don't know. But anyways, averages. How do you compute averages? What do you typically do? You add everything up, and you divide by the number of things you added up, right? Now, of course, you can't really, well, you can kind of do that. I think in some classes you can't do that, right? Because some classes, you know, your project is worth 10%, 15% of the grade, and it was out of 600 points, right? And so you can't just add those 600 points to your grade. You have to do what's called a weighted average. But typically averages, you just add up all the things, and then you divide by the total number of things, right? All right, so the issue comes, oh, this is great, this is great. The issue comes, I have this, you remember that day I had that orange ball? Do I still have the orange ball? No. I have a slinky. Okay, so here's a slinky. It's not quite an orange ball. I'm sorry. Okay, so now we have the slinky here. Now, if I take the slinky and I toss it up in the air for a few seconds and it comes back down, it had an average height, didn't it? It had an average. Had to have had an average. There's average everything for sure. I'm just making that up. But anyways, it had to have an average height. So now, let's just do some playing around here. What is, if I toss the slinky up, so what I want to know is here's me, I'm tossing the slinky up, it goes up, it comes down, and I want to know the average height of the slinky during the toss, because it was all different heights during the toss, right? There had to have been an average height. What was it? Does that make sense? Does anybody know what we need to know to figure this out? It's not too bad, actually. What sorts of things do we need to know to figure this out? Maximum height. We would want to know the maximum height, or we want to know the time, right? We're averaging over period of time, right? So it's just taking a little longer up here. We can't just take the height and divide by 2. That would be a tempting thing to do, right? We just take the height that I toss it up. About how high did I toss it? How high? About 9 feet. Let's do it in metric, please. 3 meters. Are we counting my height too? Okay, so 2 meters. So I toss this thing up 2 meters, okay? We toss it up 2 meters, and we want to know the average height that is. Now, a tempting answer. What's the tempting answer? Tempting answer. We take this. We'll make this 1 meter, okay? The tempting answer is that the average height is tempting answer? 2 meters, right? Because what you do is you say this divided by 2 is here, so it's 1 meter. Answer, 2 meters above ground, okay? That's the tempting answer. Now, this is not what we're talking about because we're talking about average height per time period, right? So now what we need to do is we need to figure out how long the slinky was in the air. All right, let's figure it out. I hope this conversation isn't too abstract. We'll see what happens. Now, what's the acceleration due to gravity? 9.8 meters per second. Did you ever notice that's about 10 meters per second? I wasn't going to say that. Did you ever notice that 9.8 meters per second is about pi squared? You ever notice that? Huh? You should get your calculator out and square pi. Is that a coincidence? I don't know. Anyways, so now, it's not a coincidence. It comes from the fact that the meter was picked by the length of the pendulum whose swing was 1 second, okay? And so if you think about the period of a pendulum, you can argue that the pi needs to appear there, and so that basically, that's why it happens. Anyhow, acceleration due to gravity is about 10 meters per second. That's what we're going to approximate it to. Okay, and which direction does it point? Down, 10 meters per second down. Okay, now, we're assuming that I tossed it from a height of 1 meter, right? And it should go up to a total of 2 meters, right? And it should do it in a fair amount of time. Oh my God, how the heck am I going to do this? I'm not going to worry. We're just going to figure it out. Okay, so now, a of t, that's our acceleration, that's equal to minus 10. Thank goodness, okay? Now, velocity of t, I have no idea how fast I tossed this thing up, right? I have no idea, all right? But I do know that after about half a second, or maybe 1/1002, let's say it took 2 seconds for me to toss it up and get it down. Does that make sense? 2 seconds? Okay. So, toss it up, and it took 2 seconds. 2 seconds. I have no idea what's going to happen here. Okay, so 2 seconds. So, I toss up the thing for 2 seconds. Oh, accelerate. Okay, velocity. Velocity of t. How do I get the velocity? Does anybody know how I go from acceleration to velocity? What do I? Yeah. And what do I do? Yeah. What do you want to? You take the antiderivative. You take the antiderivative. I know we know formulas. We've seen these things before, but we really want to take the antiderivative. And so this is going to be minus 10t. Okay, the t's time, and it's plus v0. Now, I don't know v0. All I know is how high the thing went and when it came down, right? I know how high this thing went. Okay, position of t, which is sometimes s, but I'm going to use p because it makes more sense. Position of t is going to be, oh, by the way, I didn't charge the batteries in this thing. My voice might be gone by now. Oh, I'm good. Okay, anyhow, position of t is equal to minus, oh, we got to integrate this thing again. Anti-differentiate, right? What is it? How do I anti-differentiate minus 10t? What do I get? Minus 5t squared. When I take the derivative, right, I'll get my 10t plus v naught t plus p naught. Oh my gosh, I know some of these things now, right? What height did the slinky start off at? 1 meter. This is supposed to be 1 meter. I know it might not be 1 meter, but make me taller or shorter. Use anesthetic. Okay, so now we have to put in the 1 meter here. So this is equal to minus 5t squared plus v naught t plus 1, right? Ooh. So now let's just make the whole trip equal to, we want the whole trip to be equal to 2 seconds. Yes, I'm sorry. Oh, it's just because she said, why did the v not go from plus to minus? And my plus symbol is terrible. There we go. Now it's still plus. We're tossing upward. That's what we're doing. Thank you. Okay, so if we have this, let's say we're going to have a problem here because we probably can't insist that this thing took 2 seconds and went up 2 meters. Which one do you think is more right? 2 meters or 2 seconds? First person to answer has it. We got it. 2 seconds didn't happen. Never. It's gone forever. I will digitally remove all of this from the video. I'm not going to do that. So now, okay, so now it's 2 seconds. So we want the entire trip to be 2 seconds, the trip from up to down. Great. So we have to figure out, this is a quadratic equation. How many roots does a quadratic equation have? 2. Those are when it is, well, we actually don't want the roots. We want, right, I did that wrong. Right? We want to know when this thing's equal to 1. So this plot is going to look something like, when you plug in 0, what do you get out here for t? Plug in 0 for t, what do you get out? 1. So we're going to go here. So t equals 0 equals 1. And so we want to know when this thing is equal to 1. So I want to solve 1 is equal to minus 5 t squared plus v naught t plus 1. Okay, fantastic. I can solve this thing. I've been paying attention in school, and quadratic formulas, you know, in the year 2000 BC, they were actually really hard to solve, but we got pretty good at them then. And then it wasn't until like, about that time. Okay, so anyways, so we have 0. Oh, this is super easy to solve too. 0 is equal to minus 5 t squared plus v naught t. What's the best way to solve this thing? Factor out a t. Factor out a t. 0 is equal to t times minus 5t plus v naught. Okay, this t is the time 0 when I tossed it. And so 0 is equal to minus 5t plus v naught. Okay, what's v naught? Oh, I do need that 2 in 2 seconds, don't I? Don't I? No, I don't. Yes, I do. Oh, it's v naught's equal to, no, I need those two ideas. Fantastic. Okay, so we said 2 seconds, and we want v naught plus v naught. So I have to know, let's just say 2 seconds. Okay, I'm sorry, I'm changing it to 2 seconds. You're like, I can't follow this anymore, Bart. I hate you. I'm sorry. I'm apologizing, okay? 2 seconds. There we go. So, entire trip took 2 seconds. Here we go. What's minus 5 times 2? Minus 10 plus v naught is equal to 10. V naught is equal to 10. Okay, so now I know that my initial velocity was 10, so I have p of t is equal to minus 5t squared plus 10t plus 1. Okay, this formula is supposed to give me the height of my slinky as I toss it up. Great, fantastic. So what's the maximum of this thing? What's the maximum height of the slinky? How'd you get that? But okay, whoa. Okay, so he said 3 meters, 1 meter plus 2 meters, but I said we can't do the 2, we had to switch it to 2 seconds. I know you guys said 2 meters, we had to change it. Look at the formula. Okay, let's start over. Okay, don't worry, we're doing great, okay? So, I toss a slinky, 2 seconds about, minus 10 meters per second down. Acceleration is minus 10. Velocity is this plus v naught. Position is this plus this plus this. Now, I know that when I toss it up at 1 meter after 2 seconds, sorry, I had to enforce the 2 second rule here, okay? After 2 seconds, I caught it, and so now I started solving, and I found that v naught is equal to 10. So now I'm asking, what's the maximum height? We can't just enforce that anymore. We have to figure it out. How do you find out the maximum height? What math from what class do you use? Math from what class? No, this class. This class. Math from this class. We're doing calculus, right? Yeah, derivative. We take the derivative. So, oh, we already took the derivative. This is equal to minus 10t plus 10. When does this thing have a root? When t is equal to 1. Ah, well, of course it has a root when it's equal to 1, because when you toss something up, it's symmetric, right? Oh, what's the height when t equals 1? T squared is 1 minus 5 times 1 is minus 5, so it's going to be 10 times p of 1. Whoops. P of 1 is equal to minus 5 plus 10 plus 1 equals to 6. Okay, so I'm tossing this thing up a little bit higher. Let's do 1 1,000, 2 1,000. There we go. That's exactly what's happening. So this is 6 meters, right? And there it's the 6 meters. Okay, great, fantastic. And what was the original question? Oh, what's the average height? We're finally there. Finally. How do we compute the average height? We can't cut up the time into little pieces very easily, right? I mean, we could try to do it with stopwatches and stuff, and this is something you might do in 8th grade or 9th grade or 10th grade or high school or college. But we're going to do something else. We're going to use go ahead. We're going to use calculus, right? And we're going to use the fundamental theorem of calculus. We're going to use an integral to compute average value. Average value is computed with a sum, and then you divide by the total number of things, right? What's this symbol remind you of? A violin, yes. And what sort of sound does a violin make when you don't wax the bow? So now, what does that remind you of? Sleeping, yes. And when you're sleeping, sometimes Z's come above your head, right? Which remind you of snakes, which make a hissing sound, which are S's. So sum, right? This is like sum, okay? This is a sum, the average value. So how do you compute the average value? What you do is this. You do 1 over b minus a to b, f of x dx. This is the average value of f on the interval from a to b. We're going to use this to find the average height of the slinky as I toss it. This is what you have to do when things are continuous, when they're moving smoothly. So how long was the slinky tossed into the air? 2 seconds. So we're going from 0 to 2. What's the formula for the position? It's minus 5t squared plus 10t plus 1 dt. To compute the average height, you do 1 over 2 minus 0 times this thing. This is exactly like the standard average value formula that you've known since 4th grade. Except now we're using an integral sign. The integral is the adding of the function all together. And then you divide by this range here. Okay, so let's do this. We can compute this. This is totally within our grasp. Okay, so let's figure this out. I'm going to erase my schematic diagram. And we're going to compute this integral. And we compute it using the fundamental theorem of calculus. This becomes 1/2 times the integral from 0 to minus 2 of 5t squared plus 10t plus 1 dt. Okay, what's the antiderivative of minus 5t squared? Yo, what's up? Why is it what? It's because I got overexcited with my minus signs. That's not supposed to be minus 2. That's regular 2. Okay, so now let's anti-differentiate this. I'm just going to start doing it. Here we go. It's 1/2 times minus 5 to the t squared. That's going to be minus 5/3 t cubed, right? Plus 5t squared, right? Plus t evaluated from 0 to 2. What happens when I plug in 0 here? What do I get? 0. Let's hope this answer is less than 6, right? If it's not less than 6, what happened? Why does it have to be less than 6? 6 is the maximum, right? It has to be less than 6. Okay, let's see what happens. So this is going to be 1/2 and minus 5/3 t cubed. That's going to be minus 5/3 times, what's 2 cubed? Thank you, thank you. 8 plus 5 times 4 is 20, okay, plus 2. That looks great. Okay, 5/3, 8. Jeez. 5/3, 8. Well, let's keep it there. Okay, so now let's multiply everything by 1/2. That's going to be minus 5/3 times 4 plus 12. Isn't that right? Let me just think for a second. Plus 11. Right? And now, this is 11 here. This whole thing is equal to 4 times minus 5, which is minus 20, all over 3 plus 11. Somebody estimate minus 20 over 3 for me. -7, I like it. -6 something, -7. Okay, what is -7 plus 11 equal to? That's right. I was thinking it was equal to 5, but it's actually equal to 4. Okay, so can anybody tell me why this makes sense for the average height, 4 meters, of the slinky if I toss it 1 1,000, 2 1,000? Yeah. Because I'm never at 0, okay. Let's go, yeah? It slows down towards the peak, right? And then it starts to go faster. So it's spending less time down here. This is where the integral really starts to hold its own in this sort of idea, right? Now, just for completeness, what questions do you guys have about that? That was my idea of a review. You might have said, why did we go through all that? I was reviewing everything. Awesome question. He says, why? I thought when we took antiderivatives, we had to have c's around. Now, I'm going to give a more answer than you want to hear. Okay, I'm sorry. First of all, we did have c's. This was our constant. This was our c here, right, when we took the antiderivative. And we also had another one here when we took it again, right? But his question really was, when you went from here to here, you didn't have a c, right? So pretend I did. Suppose I add c, and I evaluate from 0 to 2 right here. Then you're supposed to subtract. And the c's will always cancel. Yeah, what's up? P of t, sometimes called S of t, for position. Is it always going to be the same? It's always going to be minus 4.9 t squared plus v naught t plus p naught. Yeah, and in fact, if you're taking physics, you might just see that formula in your textbook. It's okay. Good? So, average value. What's another word for average? Mean. Okay, so if you think about mean, and in context of this class, and you don't think about any people in this class, what theorem do you think about? Mean value theorem. Okay, so the mean value theorem says that if you have some weak conditions on your function, if you have f of x differentiable on AB, right? If you have f of x differentiable on AB, there exists C. Sorry, I won't use the backwards crazy C. There exists C in C A less than or equal to C less than or equal to B with f prime of C equal to f of B minus f of A all over B minus A. This is the mean value theorem, right? All right. There's another one. There's a second one. There's the integral mean value theorem. So let's write that one down. Yeah, of course. And if you're feeling really calm, really calm, you can just, and you know the mean value theorem, you know the integral mean value theorem, because it just says this: f of C equals 1 over B minus A times the integral of f of B, f of x dx. And you might say, what the heck is going on? Fundamental theorem of calculus. What does the fundamental theorem of calculus say that this thing here equals? The antiderivative, capital F of B minus capital F of A, divided by B minus A is equal to F of C, right? These are the same thing, right? Because this is the derivative of this. This is the derivative of this. They really are exactly the same thing. If I could write a question for your exam, I'd say explain how the integral mean value theorem is the same as the regular mean value theorem. Don't worry, I think there's a 0 probability that will appear in your exam. Does that make any sense? Vaguely, think about it. Not too hard. What do you have? One more homework assignment? Yeah? Okay, good. Good, that sounds nice, right? Right? I think so, yeah. Yeah, okay, good. All right. Now in the remaining minutes, we have a couple more minutes. We're going to do one last problem. And if we get done with this problem early, we can go home. I'm just a sucker for this type of problem. I think it's a really cool problem. What? Okay. So you guys know, of course you guys are aware that we are living on a ball that's floating around a nuclear furnace that's flying through space, right? And we're basically kind of falling around this ball, okay, around this nuclear furnace. And you might ask yourselves, how far are we away from the sun, our favorite star? We really do love the sun, okay? Because seriously, it gives us all our energy. Without it, we have nothing. So anyways, the sun's awesome. How far away are we from the sun? Well, you need to know a couple things. You need to know something about ellipses. Okay, so here's B. Oh, that's not B. Here's A, and here's B. The formula for an ellipse: planets travel an ellipse around the sun. It's almost a circle, but it's not, and it's ellipse. Don't get that confused with eclipse. That's what happens when the sun and the moon pass in front of each other and cool stuff like that. So ellipse, x squared over a squared plus y squared over b squared is equal to 1. This is the formula that draws this ellipse. Of course, this is one of those bad formulas that you can't really type into your calculator, right? You have to solve for y first, and you can't do this. Yeah, I understand. That's frustrating. Okay, so we have this. And if you go to Wikipedia and you want to know how far away the Earth is from the sun, it can't tell you, because the Earth's distance from the Earth to the sun varies. Sometimes the Earth's closer to the sun, sometimes it's farther away. Do you guys know when it's closer to the sun? What? At the ends of the ellipse, that's exactly right, because the sun is kind of like here. Sorry, the sun's not there. I'm not sure if I made that. That's the center of the ellipse. The sun's like here. Boy, I just fell out of love with this question. But that's okay. Does anybody know when we're closest to the sun? What time of year? We're closest to the sun in wintertime, actually. Yeah, the southern hemisphere is closest to the sun in summertime. What? He's saying no? Okay, so let me just recap. So I'm pretty sure the northern hemisphere is closest to the sun during our winter times. And he's saying no, that's not true. Really? Well, maybe I'm wrong. Maybe we're both wrong. I don't think we can both be right. Okay, anyways. Okay, so there's some debate. So you guys should figure this out. And then when you're hanging out with your friends, you can give them a fun factoid. Okay? And then if whoever's wrong, just say I was wrong. Okay? And then you can laugh about it. That's funny. Okay, so anyways, we want to know the average value of a planet as it travels along this arc to the central point. And that's why I just fell out a little with this question, because who cares how far away the planet is from the central point? What we care about is how far away it is from the sun. But that's okay, that's a different story. So we want to know how far away a planet is, the average value here. Shoot, how do we do this? We have this crazy formula. And average value is this integral thing. Well, the book gives you a hint. By the way, this is a question in the text. It's number 49 on page 375. So you can read, this is 49, page 375. So here's the idea. What we're going to do is we're going to integrate from 0 to a. We're going to integrate from 0 to a. We're going to do it completely in general. So it's going to be 1 over a. We're computing the average value. We're integrating from 0 to a. Because I think if I compute this average value, it's the same as computing that average value. And then I'm going to compute the distance here. What do we use to compute the distance? The distance formula, right? We use the distance formula. Okay, and we're integrating from 0 to a, we're integrating with respect to x. So we're putting different values of x in here as we go from 0 to a. So all we really need to do is solve for y, and it will give us our average height, right? Well, this is interesting. Okay, solve for y. So let's solve for y here. So, y squared over b squared equals 1 minus x squared over a squared. That's nice. And then I divide everything. I multiply. I got to multiply. Y squared equals b squared minus b squared x squared over b squared. And I'm going to, the problem says they want to know the average distance squared. Can somebody give me a formula for the distance now? If we know that y is equal to this, what's the formula for the distance? It's square root of x squared minus, right? So the distance squared is going to be this. So it's going to be a squared plus b squared x squared over a squared, because this is equal to y squared. And if I take the square root, that's the distance. You guys with me here? You might have to think about this later on. I don't know. Is this too complicated? Someone said no. I don't know. So anyways, we put this in here. This is a squared plus b squared x squared over a squared. And we're supposed to integrate this thing with respect to x. First question, can you integrate this? Next question, what are the variables here? X is the only variable. Everything else is a number. And numbers are easy to integrate. They never screw you up, okay? Variables and functions of variables are the things that mess you up. No matter what sort of number configuration we have, it's never going to be a problem. So now, let's integrate this. It's going to be easy, I promise. Here we go. First of all, it's going to be 1 over a times, I'm just going to do it all in one piece because I can, evaluated from 0 to a integral of a squared with respect to x. It's going to be a cubed over 3, and then this is going to be plus b squared x cubed. Oh, no, 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 no. It's a squared x. A squared x. That's our answer. We're done for today. I don't think you guys, if you want to come up and talk to me afterwards, you can, but we're done. Have a nice day, everybody.